Hello, everybody. Welcome to the day 5 of the Open Source Tools for Chemistry Symposium. Today we have Greg Landrum, who's going to be giving an introduction to Knime workflows. Knime is a workflow tool that understands chemistry, which is absolutely critical for these sort of things. Greg is one of the real experts in this area, and so we're very grateful for him to come and give us this introductory workshop. So Greg, I'll now hand over to you.
Thank you, Chris.
Yeah, just to say that if anybody has any questions, please put them into the questions box, and I'll then relay them to Greg to answer.
Hopefully my screen is sharing now, is that right?
Yeah, see it fine.
Perfect. Okay, let me figure out. Go to arrange, go to webinar. Okay.
You might like to put it in full screen mode if you can.
Yeah, I'm about to do that.
Thank you.
Great. Welcome to this this webinar or workshop. What I'm going to do is talk about doing interactive and automated chemical data analysis using Knime. So for people who, hopefully everybody knows what Knime is. If you don't, I'll give an introduction as a part of going through the demo, but hopefully you know what it is, and hopefully if you actually have Knime installed, you'll be able to follow along with what I'm doing. So the workflow that I'm going to be working with is available for you to download, and actually what I'm going to do is, let me copy this link into the chat so that you don't have to type it out. No, sorry. Okay, so there's a link in the chat if you want to follow along. When you go to this page, I'll go ahead and stay here. Actually, if you click on the link, you'll land on this page. This is the Knime Hub. I'll say a little bit more about the Knime Hub in a moment. But from this page, you'll see there's a workflow that you can download and a data folder. Rather than downloading them separately, what's better is if you just click the download button here, and then you can download the whole group, which is the workflow plus the data. So I'm going to click that, and I now get this .knar file. Knar is a Knime archive. If you have Knime installed, when you open this file, it will directly go to Knime and offer you the option to import the data and workflows from that file into Knime itself. So what I'm going to do is it wants to install in my local folder. I will let it do that. And now I have in local, I have this workflow group 2020-1113 RSC Open Tools for Chemistry. If I expand that, I will see the Tarsiva Enabler Network workflow. I'm going to double click on that, and that will open the workflow, and we're going to work with this. I will come back to this in a moment. I want to say a few words about the workflow before we dive right in. An important thing, if you've just installed Knime or if you don't have all of the nodes that this workflow requires, when you open it, it's going to ask you if you want to install the additional software that's being used. And you should go ahead and say yes and click through that. This is only using free and open source tools. Knime itself is also open source, but we're using here completely open source components. You don't need to worry about licenses to install these. You can install them. Click through. When it's done installing the nodes that you need, it'll ask you if you want to restart Knime. Just say yes, and then it'll restart, reopen, and you'll have the workflow, and we'll be able to work with it. So we'll come back to this in a moment. Right now, I'm going to go back into my slides, and we'll talk a little bit about the workflow, what the workflow is actually doing. The problem that we're going to solve is the hypothetical problem, which is actually one that happens fairly frequently, is you are looking around and you found an interesting patent, and you would like to get an overview of the chemistry that's present in the patent. So for example, you find a patent on Google Patents where you can download the chemistry, or on SureChemble where you can download the chemistry. Both of those are free resources. Or if you're using one of the commercial resources like get a CSV file or an SD file that has all of the molecules from a particular patent. If you look at those, particularly if the data comes from SureChemble or Google Patents, it tends, if you look at the structures, that tends to be that many of them are fragments or building blocks, and depending upon what you want to do, probably not super interesting. So you'd like to have more the real molecules. There's also, whenever you download these things, there's no indication in the download of which of the structures in that data dump are actually interesting or relevant. So it's often nice just to look through those structures, or it would be nice if there was an automated way to look through those structures and come up with something, some sense of which of the structures are actually interesting or relevant. If it's a patent for a drug, or drug that's in clinical trials where the structure hasn't been disclosed yet, it would also be nice, or the structure hasn't been publicly disclosed, it would also be nice if you could find which of the compounds in that patent is the drug, because that is one of the most interesting ones, of course. The classic approach to doing this was published back in 2008, or the first publication about this I'm aware of was published back in 2008. Is to find the most interesting compounds by looking at the ones that have a large number of neighbors. So you calculate the similarities, the chemical similarities, using some kind of fingerprint between all the compounds in the patent, and you just pull the compounds out that have the largest number of neighbors. This is very straightforward. It's easy to do. It's well validated. If you go and look at the paper, they validated it quite well on a number of, I think, 20 different patents. And it gives you a small set of compounds for any given patent. A thing that's worth adding about this particular approach is it was published in 2008, and this approach became reasonably popular. So people started doing this in order to find the key compound in patents. And the patent attorneys who write patents at pharma companies or at universities learned about this, and they have now taken preventative measures that cause this method to often not work so well. So if you try the approach described by Hattori et al. On a modern patent, something in the past 5 years, it tends to not be as effective as on the patents before this paper came out. And that's just because the patent attorneys, the people writing these patents, they don't want you to be able to do this, right? They are attempting to obscure the key compounds in the patent. So they basically, I hypothesize, I don't know this for a fact, but I hypothesize that they're trying analyses like this on the compounds that they're thinking about including in the patent, and then adding things in to obscure the interesting compounds. I don't know that that's true. As I said, I have just noticed that this approach is now considerably less effective than it used to be. So we'd like to try something a little bit different. So there's this minor refinement, and it's a surprisingly minor refinement that actually does work, at least in my hands, which is instead of just calculating the neighbors of each compound, I build a network based upon that. So any compounds that are neighbors are linked in the network. And then I do network metrics. And the specific network metric that I'm doing is to calculate the hub score of each compound, and then rank the compounds by hub score. In these undirected networks, so it doesn't matter, there's no sense of which direction the connection between two compounds are, they're just related to each other. In these undirected networks, the hub score is really determined by the number of highly connected neighbors. And if you think about that, each node is determined by the connectivity of its neighbors, and of course the connectivity of the neighbors are determined by the nodes, so there's a recursive procedure here to calculate the hub score. It is conceptually similar to the PageRank algorithm that has been described for how Google used to rank the search results. But anyway, there's numerous network analysis packages that provide this hub score calculation. So my process is I set up a workflow in Knime, and I'll show you that workflow. Ran compounds through it, calculated generated these networks, calculated hub scores, and then look to see how many, look at my hit list and see how many of those contain the patented compound. So the way I did my validation, this is very kind of hand wavy, but I think it's reasonable. So what I did is I started with the Chemical list of marketed drugs. I removed drugs that violated the rule of 5 using a Chemical label, just so I don't have anything that's huge, so something smaller. No biologics, please, no peptides. I take the 25 that were most recent, and then 19 of them ended up being something that I could work with. Then I did a SureChemical search. These are all manual steps. I did a SureChemical search using those 19 structures and picked the oldest SureChemical patent that contained each of those drugs and downloaded the structures from that patent just from SureChemical, so exporting it as a CSV file. I then ran that list for each patent through my workflow and defined success to be the marketed drug is present in the first 10 compounds after I sort by hub score. This is a little bit stricter than the validation procedure used in Hattori at all, just so you know. With the 19 that I did, that worked for almost half of them, so eight out of the 19. Okay, I'm being nice. Not quite, almost half. 8 out of 19 it worked for. And it's worth pointing out that 16 of the 19 have the marketed drug in one of the first 3 clusters. So if you look at the clusters of compounds in the network, this works for 16 out of 19. This looking in the clusters is closer to the validation that Hattori et al. Did. Anyway, this is an approach that works. It seems to do a pretty good job of ranking interesting compounds towards the top, which is the thing I'm most interested in. So it seemed like something interesting to do. What I'd like to do, though, is make that whole process interactive. So the validation shows that the approach is not complete nonsense, and it shows that I can automate it. Now let's look at how to do that, but also how to make that interaction, that interactive version, useful. And I'm going to do the whole thing, of course, using Knime, because this is a Knime presentation, and the RD kit, because I do everything chemistry related with the RD kit if I can. So let's go in and look at the workflow. Before I do that, Chris, are there any questions so far?
No, everything's fine so far. I put a couple of links in the chat, and I'll put one into about RD kit as well.
Thank you. Okay, we have a high-level overview of what the workflow does. So actually, let me give a quick overview as to what Knime is before getting into that. I always use Knime because I use Knime a lot. I use it in a view that is not the default. Let me set it back to the default view. If you guys are using Knime and you're using it for the first time, you'll get something that looks like this. So what you have over on the left-hand side, there's the Knime Explorer, which is a tree that has your workflows and organized into a tree structure. There's the Workflow Coach, which is a system based upon an analysis of workflows that we've seen, that we've built, and that members of the Knime community have built, that provides recommendations for which node you might want to use next. At the moment, I don't have any nodes selected, so I'm just getting generic suggestions for starting a workflow. And you see the suggestions here are about reading files or reading from a database, or connecting to a database, which is what you would expect, right? If I'm going to start working with some data, I need the data. If I select a node that reads data in from a file, you can now see that I start to get suggestions based upon actually doing something with the data. So the Workflow Coach is a useful way to, if you don't know Knime at all, it's a useful way to get a sense of what you might want to do once you have a node present, or the kind of things that are possible to do if you have a node present. And as I said, this is based on a statistical analysis of workflows that we've seen before. So in modern language, it means this is AI. It's just a statistical analysis. Anyway, below the Workflow Coach, you have a node repository. This is a list of all of the nodes that are available for you to work with. There are lots of these. Depending on how many extensions you have, there may be 2,000 of them or more. Actually, we're also up to almost 3,000 at this point. We try to organize them in a reasonably self-explanatory way, but this is never perfect. In the end, the way you often end up finding nodes is just by searching for them. So if I know I want a row filter, I can search for row filter, and then it shows me all of the things that have row filter in their name. So the node repository is where you get the nodes. You can add a node to your workflow by just dragging it out onto the workflow. If you have a node selected already, you can double click here and it will add the workflow connected to the node that you have selected. You can also drag a node in and drop it on a connection and it'll insert it in the connection. So those are all ways that you can use to add a node to your workflow. Good, other pieces here. This is the canvas that shows you the workflow itself. You can move around on here and zoom in and out. We're gonna spend most of our time working in here. Off to the right is the description. If you click a node, you can see the description of the node itself. So you can see a description of what it does, explanation of the options that it has when you configure it, and then an explanation of what the input and output data for that are. So this is a useful way as you're browsing through nodes in the node repository. If you're not sure if a node does what you want, the node description can help you with that. Down at the bottom, there's also an outline, which gives you a high-level view of the workflow. I find that useless, so I turn that off. And then the console, which is if you end up with errors or messages from any of the nodes, they show up here. I also don't generally want to see this, so I tend to make that go away too. So the way I normally look at Knime is I would get rid of this bit down here, or at least make it really small, and shrink the description down. I really want to see the workflow, right? The workflow is what I'm going to be using for most of the time. I also don't use the workflow coach, and I put the repository next to the Knime Explorer because I don't ever need to be looking for a workflow and nodes at the same time. So this is kind of how I normally look at Knime. Let's look at the workflow and I'll give a high-level overview of what it's doing, and then we'll go in and look at it in detail. So we start by reading data. This is just using a normal Knime node. The file reader, if I double click on that, I can configure it and see the configuration options. Here we go. You can see the workflow that I'm reading. In this case, it's reading, I'm using a Knime URL for this. This is sorry, let me change the view a little bit so we can actually see what this is referencing. I have my workflow over here. So this is the workflow. So when I configure it, if I'm using this Knime URL, it starts by referencing the workflow, so knime.workflow, and then it says look in there and find the file tarsivachemistry.csv. This is a file that I distribute with this workflow itself, just so that whoever gets the workflow can immediately start to use it. You can't actually see it over here in this Explorer, so what I'm gonna do is switch to a different file, and I'm gonna switch to a file that's in the data directory. Before I start changing anything, I know that I exported all of these files from SureComble, so I know that they all have the same column structure. So I'm going to start by clicking this preserve user settings for new location. This way the information about the columns that's down here will be stored and I don't need to enter any of it again. So I'm gonna start with the Knime workflow. I'm gonna go up one level by doing ... Now I'm in this folder of the workflow tree. So in the upper next folder up, I will then go down into the data folder and I will pick Tarsiva chemistry.csv from there. And you can see I get a preview of the file down below.
It might be just worth explaining to people who are not comfortable with the command line why ... comes about.
Okay, ... means go up one directory. If you don't like this, if dealing with this makes you uncomfortable, you can always just browse to the file. Right, so I can always just browse and pick a file. The reason I did not do that is the nice thing about these Knime URLs is if I save my workflow now and send it to someone else, this will work for them. If I browse and it actually puts a path to the file in here, so if it says c/user/G Landrum/ blah, 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 then if I send it to somebody else, it's not gonna work for them because it has a path in it. So these Knime paths are relative to the workflow, and it means as long as the user gets the workflow and the data directory, everything is going to work fine. Again,
Thanks.
dot means go up one level, and then I then go into the data directory. And over here, you can see what that level is. So I'm at the workflow, dot, I go up, so I'm here, and then I go down into data. Okay. So let me execute that. What I did execute that is I right-click to get the context menu and hit execute. I could have also, let me reset this. I could have also up here clicked the green button, the play button to execute it. Or there's a hotkey for that too. I can never remember what the hotkey is. So I just do this by right-clicking normally. You can tell that the node is ready to execute because the status is yellow with the little traffic light at the bottom. If the status was red, then it means there's a configuration problem and it's not going to work. So this one is yellow, it's ready to go. So let me go ahead and execute that. The node has a port here, the output port. And if I hover over that, you can see it tells me the number of rows and columns, so I get a quick sense of what the data looks like. I can also right-click on the node and have it show me the table. And you can see here a view of the data. So I have a string column with the patent ID, a string column with annotation, a string column with a Schur-Campbell ID, a string column with smiles, and then some other information. And this all just came from Schur-Campbell. You can here in this view, you can sort, so I can change the sorting. And there's another tab, which is the spec, that allows you to just get a sense of what all of the columns are at once without having to scroll. So you can see these are my 28 columns, and these are the types of those columns. For numeric columns, you can also get a sense of what the data are like. So for example, the molecular weight in this case, in this table goes from 13 to almost 1,200. The ring count goes from 0 to 12. So it's nice to get a quick overview of your data here.
I have a quick question.
Yep.
Is it possible to show the structures rather than just the smile strings?
It is, and I'm going to show you how to do that right now. Thank you for the question.
Okay.
So something went wrong when I configured this node. I had clicked this preserve user settings for new location, and it didn't do what it was supposed to do. So I screwed something up. What we need to do, down here in the preview, you have all the columns. You can see it's read the column headers from the file. So there's a smiles column. The type of this is string, and I need to tell it that the type of this should be smiles. So I'm going to click on the column header, and it allows me to change the name if I want to, but I can also change the type. I'm going to change the type from string to smiles. Click OK. And now it knows that that's not a string. Now it knows that that's a smiles, and it shows me structures. So let me say OK. I'll execute the node again. I will look at the output port, the output data. And now you can see I'm seeing the smiles. It's using the renderer to show me the smiles. If for what, sorry, let me also show you can resize this, of course. If you shift resize the rows, it'll resize all of them. So now I can get a sense of what the compounds in the data look like. If you do not want to see the pictures, because for whatever reason you want to see the smile strings themselves, you can right click on a column header and change the renderer to string. And then you can see the smile string. This is sometimes useful for debugging purposes, but generally, if you're a chemist, you want to see the string, the molecule pictures. Okay, so we have a table of data. You may have noticed as we were looking through that there were things in there that looked like potentially interesting molecules, but I also remember that there's water in there and ammonia and stuff like that. So I'd like to filter the data down, and I'm going to filter based on computed descriptors and physicochemical properties. So the first thing I'm going to do is do some pre-processing of the data. And what I've done is I have a bunch of nodes that do pre-processing buried in this meta node. This dark gray node with a kind of hard box around it is called a metanode. And this is just a packaging of a bunch of other nodes. So I'm going to double click on this to open it, and we can see what's inside. So inside the metanode, you see that there's a graphic over on the left-hand side that has the data coming in. There's a graphic on the right-hand side that represents the data table going out. And in the middle, there's just another collection of Knime nodes. So this metanode is just an organizational thing, right? It makes it so your workflow looks nicer. You can understand what's going on better. So let's look at what we're doing. The first thing I'm going to do is some of the data, some of the compounds in here have salts with them. For the analysis that I want to do, I'm not really interested, the salts don't help. So I'm going to start by stripping salts out. And I do that using an RDKit salt stripper node. This will just go through each of the compounds and look to see if there are things from a list of common salts. And if there are fragments from the list of common salts in the molecule, it'll just remove them. So I run that. That gives me a new output column that has the molecules with the salts removed. You can see I got a warning here. The warning says that the conversion for one of the column, at least one of the rows failed, and actually tells me 7 of the rows failed. This is because there are smiles in this data set that the RDKit does not recognize as valid smiles. So if we look at the results at the end, there is a new column, which is an RDKit molecule column that has the salt strip molecule. So we can look at that. It also has an image associated with it. This also has a renderer associated with it, so I can right click and change the renderer. So if I don't want to see the molecule generated rendered using the RDKit, I can look at just string, which shows you smiles, or I can use other tools. I'm going to render it just using the RDKit, of course. So somewhere in here, there are some molecules that have missing values because the RDKit did not like the smiles. And missing values show up as this red question mark. So let's go over and look and see what this actually is. So I'm going to go over and see what the input was. No, I'm not, because I took the smiles out of the data set. So, okay. Normally what I would do here is I would leave the smiles column in the data set and go back and look at the smiles that caused the problem. We can do that later if there's time. There's something wrong with one of the molecules that we can then look at and conceivably fix.
So we have somebody's commented that the rendering as smiles still isn't working.
Okay.
Could you perhaps just go through that again? It's possible they just missed a click.
No, it's likely that the nodes that the package that they need didn't get auto-installed because I'm not using the nodes for that. So what you need to do is you need to install the Chemaxon extensions. These are free, so you don't need to worry about, well, they're free at the moment. That's going to change in a month, but for now they're free. The way you install them is you go to Help, Install New Software. And then here, you're going to click that you want to install from the Knime Analytics Platform 4.2 update site. That's going to refresh and show some stuff. And what you need is the Marvin chemistry extensions. So I apologize, you're not seeing it for me because I already have them installed. Let me change the setting. You want to install the Chemaxon and Vocom Marvin chemistry extensions feature. So if you install that, then you'll have the render for smiles. The next version of the RDKit nodes will also do this because the Marvin stuff isn't going to be free in a month, but for now you need to install the Marvin nodes. Okay, hopefully that answers the question. So again, you just click this, it'll ask you if you're sure you want to install, do you agree with the license, and then you'll need to restart Knime again. Once you've done that, you'll have the smiles renderer. So we tried to do salt stripping from the molecules. Some of them had problems. So remember there were 7 rows that had problems. I'm going to remove those rows with the row filter. The row filter I configure to look at the salt strip molecule column to exclude rows where the value is missing. So when I execute that, it is going to remove those 7 rows. So I'm down to 476 from 483. I'm now going to generate a canonical smiles because I want to remove duplicates. This data set does contain duplicates. And then I'm going to remove the duplicates using a duplicate row filter. The duplicate row filter, I just set up to use the canonical smiles to recognize duplicates. And on the advanced side, it just brings over the first row from all of the other. If you have duplicates, it only brings over the first row from the duplicates. So let me just go ahead and execute that. I intentionally did not execute the canonical smiles along the way because I just want to show you, to this point, I have been executing the nodes one by one. I don't have to do that. I can execute a node later in the workflow, and that will cause the ones before it to be executed. So it'll go back in the workflow and pull the data to itself. So now at this point, I'm down to 376, okay, from 476. I removed 100 duplicate rows from the data. The next node is an implementation detail that I apologize is necessary, but it is necessary later in the workflow. This generates an SVG or PNG image from the molecule column, and we'll use that later when we're actually looking at molecules in JavaScript views. I'm then going to calculate some descriptors. The RDKit descriptor calculation node has a long list of the descriptors that it can calculate. For this, I'm going to filter based on physicochemical properties of the molecules in the data set. So I'm just going to calculate some of the properties that I might want to filter on. So I'm going to calculate a log P prediction, the molecular weight, number of rotatable bonds, number of heavy atoms, and the number of rings. I could add other things to this, right? There's a huge number of descriptors to choose from, but these are the simple ones I'm going to use for the analysis. Okay. Next step is to generate a fingerprint. So we're going to remember the way we're doing this analysis is we're calculating the similarity between all of the molecules, and molecules that are similar enough to each other will connect and form a network from that. The similarity that we're going to use is based on the RDKit's Morgan fingerprint. Those of you who don't know this, you may have seen people using ECFP fingerprints from Pipeline Pilot. The RDKit's Morgan fingerprint is equivalent to the ECFP fingerprint. So I'm doing the Morgan 2, Morgan fingerprint with a radius of 2. I call that MFP2. That is a good descriptor, or it's a good fingerprint if you don't know that something else, you should be using something else. And it is the default generated by the RDKit fingerprint node. In general, if you get a high fingerprint with the Morgan similarity, the two molecules look the same. So it's a good chemical fingerprint for things, if you just want high similarity to mean the molecules look alike. And then we're going to remove some columns that aren't necessary for the later analysis and then rename. Let me see which column we rename. So we're going to rename, there's this column with this long name, Smiles Canonical Fingerprint. I'm going to rename that MFP2. There's a Smiles Canonical. I'm just going to rename that to Smiles. And then there's the image that we generated, salt strip molecule. I'm going to rename that to be mol image. I could have renamed each of these along the way in the workflow, but sometimes I just find it easier just to do this at the end and have all the renames in one place. Okay, so that's what's going on in this meta node. I'm now just going to close the meta node and we'll go back to the workflow. I'll just go ahead and execute that, and that'll execute the last few nodes, and then we'll get the data on the output port. This takes a little bit because that render to image node, for whatever reason, takes a while to run. Now I can look at my output table. Again, right click and show the table. And you can see what I have in here. We'll start with the columns. So I have some of the data that I ran in at the beginning. There's a molecule image, there's the smiles, and then my calculated values and the fingerprint. Sorry, I forgot we can actually look at the data itself too. So I'm fighting with my mouse now. There we go. Over on the right-hand side, you can see there's the molecule image, there's the smiles and its rendering, the calculated values, and the fingerprint. Next step is, remember, this data set still contains loads of garbage. So it contains water and ammonia and little bits and pieces of molecules, and we'd like to filter all of that out. We're gonna do that interactively, and I'm gonna show you the interactive view first, and then we'll see how this gets built. So I have this light gray node here is called a component. This also contains a bunch of nodes inside it, and we're gonna expand and look at those, but first we're gonna execute it and look at the view that it has attached to it. So I'm going to execute this, and to execute an open view, which is this button, or I can do that here as well, execute and open views. What this does is it runs all of the contents inside, and because there's a view attached to it, it opens the window that shows me the view. And what I have in this particular view, it has a number of components. So there are a number of pieces to it. There is a parallel coordinates plot, which I'll explain in a moment. There's a table that has the molecules itself. And then there's some sliders that allow me to control filters around particular properties. So let me just go back here. I'll open these all the way up so we see all the molecules. Okay, so if we hadn't done anything and we just read the data in, you could imagine getting something like this. So there's the data set contains between 1 and 77 heavy atoms, 0 and 12 rings, and 0 and 32 rotatable bonds. And it contains stuff like water and ammonia. And I can't even tell what that is. I'm guessing that's a metal with a bunch of triphenylphosphines that should be connected to it and aren't. So it's got all kinds of weird stuff in there that we're not necessarily interested in taking forward. The table over here, you can see I have the molecule and I have the computed properties. What I did to rearrange the table is I just clicked on the column header and it changes the sorting. Right, so I can sort by molecular weight, or I can sort by a number of heavy atoms, etc. You can see there's all kinds of weird stuff in here. I want to get rid of all the weird stuff and just have useful molecules. So we can think about how we might do that. So first thing, we probably want some certain minimum number of heavy atoms. So I don't know, let's say the smallest you can have is something that has at least 6 atoms. I definitely don't want 77, so let's say no more than 50 heavy atoms. You can see as I'm doing this, the contents of the parallel coordinates plot are changing. We're dropping lines. The table itself is also changing, but we don't see any of the molecules that are being filtered out, so we're not noticing that. In general, unless I'm doing polymer chemistry or some very particular types of peptide chemistry, I do want rings in the molecule. So something that has no rings is probably not going to be interesting. So let's say it has to have at least 1 ring, and I don't know, no more than 8. And I want a rotatable bond in there, at least 1 rotatable bond, but certainly not 32. So pick some random value. And by doing this, I'm just filtering down what's present. And as I was changing this, you might have seen the contents of the parallel coordinates plot change. And we can scroll down to the bottom of the table and we can see now that we have 170 entries left, filtered down from 376. So we've removed a lot of stuff from the table or from the table already. It's a lot of kind of garbagey molecules. We can get a little bit more information as well using the parallel coordinates plot. So the parallel coordinates plot allows you to filter or to select based on the columns in the parallel coordinates plot. So if I click on one of the axes and drag along it, it will select the molecules that are inside the window that you have. I'm now going to tell the table that it should show me only rows that have been selected so that I can see the things I selected over there. So you can see this is the small set of molecules that are present there. There's only 4 molecules in that window. These can be dragged around. So I can drag down and there's more molecules. And I can also select on multiple axes at the same time. So if I want these things to have a large number of heavy atoms and let's say a relatively small number of rings, I've now filtered on both of those simultaneously and there's no molecules left. So let me go down. Here we have the molecules that have a relatively large number of heavy atoms and basically a small and only 3 rings. I can just drag this around as you already saw. So I can grab the thumbnail and move it. Look at the ones that have 2 rings. You get the point. I can also click and do another column as well. Parallel coordinates plot is a really nice way to kind of filter or do selection on multiple axes in your data at the same time. As long as you have, let's say, less than 5, or maybe 7 columns work reasonably in the parallel coordinates plot. While I'm here, I might as well go ahead and demonstrate this. Another interesting thing that you can do with the parallel coordinates plot, you can use it to look at relationships between columns, which is actually what it's really for. So I'm going to rearrange the columns. The best way to look at the relationship between columns is to put them right next to each other. So I'm going to rearrange columns and put the number of heavy atoms next to the molecular weight. And then, unfortunately, we don't really see anything in here. What you see when you do this often is the line is more or less straight across, because across the range of data, it tends to be that increasing number of heavy atoms increases the molecular weight by the same amount. If you have, however, heavier atoms, if there's a bromine present or a sulfur or a phosphorus, it messes that up. And so you can see those molecules by lines that go between number of heavy atoms and molecular weight, lines that go up a lot. And unfortunately, we don't see that here because there's too much data and there are no clear lines, so it's not particularly useful. There is this one interesting thing here, which is here's a set of molecules where the log P is quite low relative to what you'd expect based on the molecular weight. You can see in general, these lines all have about the same slope, but these molecules have a very different slope. So those might be interesting to look at. And yes, in fact, you can see, so if you know how log P is calculated, this particular model does a sum of atom contributions. So if you have a lot of polar atoms, like these sugars, you end up with a very low log P. And so it's not surprising here that you have this very negative log P for a comparatively moderate molecular weight. And that's the kind of thing that you can do with parallel coordinates plot. It's a very useful plot. My colleagues at Knime always laugh at me because I generally try and get this into basically any view that I do. Okay, I can now close this and apply my changes, and it will save all of the changes that I made to widgets in the view, as well as the selection, and use that to change what goes in the output table. I'm not going to do that because I had it set up nicely when I saved the workflow before, so I'm just going to do close and discard. And what comes out of this node now is the 178 molecules. Let me go back and look at it with the default settings. So it's using a number of heavy atoms between 5 and 50, number of rings between 1 and 8, and number of rotatable bonds between 1 and 15. That gets me down from 376 atoms to 178, and we'll use those for the future analysis. But first, let's see how we made that view. So let's look at the view. This is fairly complicated, right? I have 3 of these range sliders up top and then a parallel coordinates plot and a table, and you saw that they were all talking to each other. So I changed things in one, it was reflected in the other. So this is what we're going to try and create. So 3 range sliders, parallel coordinates plot, and a table. I'm now going to look inside the component. Remember I mentioned this is just a collection of Knime nodes. So the way you look inside this is Control double click. On the Mac, that's Command double click, or you can just right click and say Component, Open. This is just like looking inside the metanode before. There's an input and there's an output. and a series of nodes. What we have here, there are the 3 range sliders. So these are, it's called a range slider filter definition. That's the node. Those are the 3 range sliders we saw. This is the one for the number of heavy atoms. This is the one for the number of rings. This is the one for the number of rotatable bonds. I could make it so it's easier to see that. We don't have to work quite so hard. So non-heavy atoms. No rings. Okay. And then what comes out of the range slider is passed to a parallel coordinates plot and a table view. And those are the 2 other views that we saw when we were looking at things. You can see I removed some columns. So the parallel coordinates plot will use every column that you give it. So I remove columns from the data set. I only want to include those columns with computed values with the descriptors that I computed. And
we have a question that's probably, this is a good time to answer. What is the difference between a component and a metanode?
That's an excellent question. We do that to confuse you. No, so a metanode is really just a collection of nodes. It's just an organizational thing. You can think of it, it's just a container. It's basically hiding those other nodes so they don't clutter up your workflow. So it's just for organization. So that's this thing. A component is much more sophisticated. A component is, it can have a view attached to it. So we saw the view that is constructed from all of the views that are inside. A component can have configuration attached to it. So if I double click on it, it can have configuration options here. That doesn't have any, but this does. So you can see by double clicking on this component, I can change a parameter that's used to build a network. And I'll show you how we build this. And components have some encapsulation attached to them. So you can really think of it as it's almost like a node. It's almost like writing your own Knime node using other Knime nodes, whereas a metanode is really just a way to hide things so your workflow looks better. The other very important thing for components is if you use them together with the Knime server, which is our commercial product, the components with these views on it, sorry, if you build a workflow that uses components and put it on the server, each of the components becomes a page in a web application. So if I were to put this on the server, when I started running it on the server in the web portal, it would do the work here, and then it would show me this view and wait for me to finish interacting with it. When I click done, it would then show me this view if there's a view attached to that component, and wait for me to interact with it until I'm done, then show me this one, and then show me that one. So components are much richer than metanodes. It is confusing though, particularly when you're first getting started. Basically, there's almost no reason to not always use components. And so using metanodes is it's simpler, but it's almost an advanced user thing because I'm saying something to somebody who knows what Knime workflows by putting things in a metanode. I'm just saying this is just organizational, whereas this may actually have views and data attached to it, views and configuration attached to it. Okay, let's look inside the component again. So then I mentioned already we have the column filter so that the parallel coordinates plot is just showing a small number of columns, the ones we care about. The table view is I'm going to use a column resorter. So it's going to show all of the columns in that, but I want to rearrange the order of them so that I see the molecules first. So in here, I had moved the molecule image up to the very top. And then the next step in this is this filter apply. So what happens here, the range sliders, they're building up a definition of a filter. So they're building up a definition, which is on this little blue port, of a filter based on the number of heavy atoms and the number of rings and the number of rotatable bonds. And then filter apply applies that definition to actually filter the table. So coming out of this slider, there's 376 rows. So coming out of the table, there's 376 rows, but when I use the filter apply, I'm down to 178. So when you're inside the view and you're changing the range sliders, it's not actually changing the number of rows in the table, it's just changing what's visible, and the filter apply is the one that actually changes the number of rows in the table. We saw that all of these tables were interacting with each other when I had the view open in the component. Remember when I changed the selection in the parallel coordinates plot, the table view knew about it because I could change the show selected rows only setting. It would only show me the thing selected here. I didn't have to do anything to have that happen. This will happen automatically in a composite view attached to a component if the views are derived from the same table. So I have this one table that comes in and I can follow through, and you can see that the parallel coordinates plot and the table view are really from the same table. Because of that, they're sharing the same row IDs, and because of that, the tables talk to each other or communicate with each other when the view is open. So those are the 5 pieces of my composite view that we saw. The next step is I need to lay those out. You remember when we were looking at that view, I had the 3 range sliders across the top, and then the table view and the parallel coordinates plot next to each other. If I don't do anything, if I just create this component, these will be laid out vertically. So first range slider, second range slider, third range slider, table view, parallel coordinates plot, and the order in which they're there is going to be determined by the order in which you added nodes to the workflow, to the component itself, which is not great. So you almost always are going to want to change this. And you do that here by using the layout editor. So from this option on the toolbar, you then get a layout editor where you can arrange the nodes the way you want to see them on the page. And you can see I've set things up here so that I have range slider, range slider, range slider, and then the parallel coordinates plot in the table view. So that defines the view, and you remember that's what we saw when we actually looked at the view. And it's important the output table from this filter apply goes to the component output so that when I so I have something to connect to the next node in the workflow. Let me just go ahead and finish executing this. And I have my 178 rows and 32 columns, and we can now move on to the next step. Before I do that, Chris, are there any questions that are built up during this?
No, do you want to just show the view again, though, perhaps, just so that people can see remember what the final result looks like?
Sure. So here's the final result. We have the molecule table. Let me sort, at the moment the molecules are sorted. Let me put the biggest ones first. Yeah. It's interesting. Oh, yeah, so the table hasn't up, that's actually somewhat strange. I would have expected the table to, okay, I need to change it in order for the table to update. So at this point, this should now be, okay, there's 219. Let me finish updating these. This is a bug, I apologize for this. Should now be down to 100, 219. Okay, now we're down to the 178. Yeah, so these are the molecules that are going to be taken forward for the further analysis.
Yeah. So it looks like there's a selection box on the far left of the table.
Yeah, that is selection. So you can select things here. If you want to see where one of these points are in the parallel coordinates plot, I select it and that changes the selection in the parallel coordinates plot too. So the selection from the table goes to the parallel coordinates plot and vice versa. I can. I normally don't do this, but you can also tell the parallel coordinates plot. I don't have it enabled. You can have the parallel coordinates plot also only show the selected rows.
Yeah. Okay, I think that's great.
Cool.
Let's go on.
Okay, so now we have the compounds we're interested in. The next step is to generate the neighbor network. And what I mentioned already, what we're going to do here is calculate the similarities between all the molecules. The molecules that are similar enough to each other, we're going to say that there's a connection between, and we're going to form a network by just taking all the compounds that are connected to each other. Those are one blob, and then compounds that are the next set of compounds connected to each other are another blob. This is easier to show than it is to describe. So I'm going to execute this in open views. And what we're going to see is the neighbor network for the compounds in this data set. So each of these blobs corresponds to a set of, each point corresponds to a set of compounds. You can see there's a bunch of connected compounds here. So these are compounds that have a certain minimum similarity to each other. And then you see there's a bunch of smaller clusters. This particular network view that I'm showing here is really just so you can get a sense of what the network looks like. The next component we look at is going to do much more with this, but this is really just to get a sense of what the changes are. It's important to point out you do not see all 178 points in here. The singletons, so compounds that have no nearest neighbors, don't show up in this plot. So this is only things that are connected to that have at least one neighbor. This particular component has configuration associated with that. We saw that already. So if I double click on it, it opens the configuration dialog, and I can change the distance threshold for edges. So this is how dissimilar two molecules can be in order to be connected. So this means a Tanimoto similarity of 0.8 is enough for two molecules to be connected to each other, but 0.7 is not enough to connect them. So let's change that. I can make it 0.3. So distance of 0.3 is a similarity of 0.7. 0.7 is kind of a pretty common threshold for Tanimoto. I can now execute that in open views, and what we're going to expect to see now is bigger clusters. And you can see, in fact, we do see that. First of all, there's more compounds in this plot, and you see bigger clusters. We get bigger clusters because it's easier for compounds to be connected to each other because we changed the threshold to make it easier for things to be considered neighbors. Okay, so that's what this node or this component does. Let me change this back to 0.2, and then we're going to go inside and see. I found, just as a comment on parameters, I found 0.2 to be a useful threshold for this particular analysis. It's not, if I just wanted to see the network of compounds, it's not what I would have done. But for this hub score based analysis to find interesting compounds, 0.2 as a distance, so 0.8 considered 0.8 similarity for things to be neighbors, I found to be better than the 0.7 that I normally would pick. So let's again double click to see what's inside this. The first thing we're going to do is we have the compounds coming in. We're going to generate the distance matrix between those compounds. So this is another metanode, and again, the metanode is just here to simplify things. So we look inside the distance matrix. This is just removing some columns. Now I want to calculate the distances between everything. I do that by defining a distance measure, which this is in this bit vector distances. Fingerprints are bit vectors, so I use bit vector distances. And I say I want to use the Tanimoto similarity. That's, for those of you not familiar with the field, Tanimoto is a classic similarity to use for chemical fingerprints. It pays attention to the features that are set and ignores the features that are not set. Once I've defined the distance, I can then calculate a distance matrix. The distance matrix calculation goes pretty quick for the set of compounds. And what comes out of this, sorry, that was the wrong button. What comes out of this is a table that has a distance matrix column. So it's for each row, it has a column that you can't really see the values of for all of these, that contains the distances between this molecule and all of the other molecules. And it's actually smarter than that. So it recognizes that it's a metric and the things at the top don't match the bottom. I'm not going to get into the details on that. You almost never want to look at this. But I do want to use the distance matrix. So I'm going to use the distance matrix with this distance matrix to network node. And what this allows me to do is I give it an input table and a distance matrix. It's an input table that contains a distance matrix. And I tell it that it should create edges between the nodes in the table, or between the rows in the table. It should create edges between those based on the distance column. So in this case, I want to create edges for everything that's less than or equal to 0.2. Okay, so distance less than or equal to 0.2 means create an edge. And the output of this is this funny port that's a yellow box. It's not a data port, but you can hover over it and you can see the output of this is a network. Then I'm going to add some additional information to the network. This is just information about the molecules themselves. You do that using a feature inserter. I'm not going to get into the details on this because we don't want to spend too much time on the network analysis components of this. There's a whole webinar we can do on that. I do run the network analyzer, and with the network analyzer, I calculate the properties that I'm going to use later. So remember, I wanted the hub score, so I want to calculate the hub score, and I calculate some other parameters around the nodes in the network as well as the edges of the network, just so we have a nice analysis of the graph for later. I join the information about the nodes back on, well, so I now have, let's look at this. From the network analyzer, I have statistics for each of the nodes. I actually have to run this. I have statistics based on for each of the nodes. The node is a row in the input table. So for row 208, I have this node degree and this node degree percent, et cetera. These are all the metrics that we calculated. What I now need to do is get the information about the rows connected to the rows. So coming out of the distance matrix, I have my molecules. Each of these molecules has a column in it, which is this compound ID column that has this row 0, row 1, row 2. The output of the network analyzer has the object ID, which has this row, the same looking things, row 0, row 1, etc. And now what I want to do is find each of the rows in this table, from the table from the network analyzer. I want to find the corresponding row that came out of the distance matrix and line the columns up with each other. And the way we do this in Knime is with the joiner. So what I say is I want to look at the object ID column from the top table and the compound ID column from the bottom table. And I want to bring all of the data from the top table across, and from the bottom table, I'm only going to bring the molecule image and the smiles. And when I do that, I can execute this, I get an output table that has the same number of rows as this top table. It has 74 rows. And these are the nodes that have been added to my network. So remember, I had 178 to start with. Only 78 were added because the other about 100 don't have a neighbor in the data set. So the only things added to the network are the ones that have neighbors. Okay, then there's a network viewer. We saw the network viewer. Remember, that was we saw the network viewer and the view on this component. That's the general flow. There's one more thing I need to tell you about, which is, remember, when we double clicked on the view, on the component, when we double clicked on the component, it allowed us to provide the distance threshold. And we did that by adding this double configuration node. double configuration, it has that label, distance threshold for edges, and it creates a new variable called distance threshold or distance thresh. I wanted to set the minimum and maximum values for that, right? Because a distance threshold of less than 0 doesn't make any sense, and a distance threshold of more than 1 doesn't make any sense. So I set those, and I set a default value of 0.2. What that does is produce a variable. That's this red port, it's a flow variable. And now I'm going to give that to the distance matrix to network node, and I'm going to use that to set this value here. So you see it says 0.2, but it's telling you down here that the threshold parameter is being controlled by a variable. I did that by going to flow variables, finding threshold, and picking distance threshold from that. So that's the flow variable defined by the configuration. So that allows me to pass this configuration from the component in to the distance matrix itself. So I change it to 0.3, it gets changed here, and that gets passed in and changed here. If I configure the node again after changing this to 0.3, this is still going to say 0.2, right? It's telling you the actual value is coming from the variable. Okay. So we execute that view. The output of this are the rows that correspond to the nodes in the network and then the network itself. Next step. Now the next view is the one we're going to use to identify the interesting compounds. So we've started by filtering out hopefully we filtered out all of the complete crap. We've now generated a network of neighbors, and we're going to use that network and analysis of it to pick the interesting compounds. As always, I'm going to start. Go ahead, Chris.
I was going to say, there was a question about the fingerprints and Tanimoto and things. So I've put a link in the chat to your UGM presentation on RDKit fingerprints and Tanimotos and things, so people can have a look at that if they want.
Okay. Yeah, I mean, when I get through this next view, or like the next two components, I think there's going to be some time left, and I'm happy to answer additional questions about that kind of stuff then. I think it would be a good time to do that.
That sounds good.
Cool. Okay, so let's start, as always, by looking at the view, and then we'll see how we built it. So we're going to get here is kind of the same pattern we've seen before. In this case, there's a range slider up at the top for the hub score. There's a view of the network, and then there's a table with the molecules. And what I'm going to do is go back to the default value here of 0 for the hub score. So the hub score is now not being filtered in any way. This is the network. We saw this before. I can zoom in on this just by doing control drag. I can go in here and pick nodes, and it'll highlight things in the mole image itself. Highlight things in this table. I can change the sorting in the table. So for example, hub score is the interesting thing here. And then I can use this to show where the compounds are. So I select a compound in the table, and I can see where it is in the network. So you can see these things with the hub score, they're next to each other. I can do selection in the network. I'm click dragging now to do this. So I select some things on the network, and then I can tell the table to only show me those rows. And I can see the members of that cluster. And you can see these are all things that are very, very similar to each other. As you would hope, they're neighbors. Let me zoom back out here and reset the selection. So this is where we start. One of the things I noticed in looking at this is that all of these little bits and pieces down here have a low hub score. They actually have a very, very low hub score. And so what I can do is with the range slider, if I just start at 0.01, I get rid of almost the entire network, and I just have this one kind of central cluster of the most interesting compounds. This has been true in almost every patent I've looked at, that setting this hub score of 0.01 gets rid of almost everything except for one cluster, and that cluster is the most interesting one. There are exceptions, but this works really nicely to narrow things down. We already saw we can sort by the hub score, so I'm going to do that. And if we go over and look at the compounds, this is the patent for Tarceva. This is Tarceva, so it's the third ranked compound in the data set. You can see the ones that are near it are all very, very similar to it. Right? These are just the methoxy versions of the two above. Here's an ethoxy version instead of methoxy, but the compounds that are in this top cluster are all very, very similar to each other. And this, of course, I'm going to pick an example. I'm going to pick an example and show it to you for one that works. So Tarceva works really, really nicely.
I have a quick question.
Yeah.
Can you label the nodes in the network plot?
I can add text to the network plot, but I cannot put the molecule images in, right? What you would really like is not to have this table here.
Yes,
What
just
I would
hover over a point and have it pop up the image.
Yeah, or worst case, you click on it and it pops up the image, but we haven't gotten there yet. I hope that that'll show up at some future point, but I'm not gonna say when that would be. We don't even have people working on that at the moment. So at the moment, it's the interactivity with the table is really not optimal. But sorry, the interactivity with the network is really not optimal. It would be super nice to be able to have those be maybe even have molecule pictures here, but at the very least that you can hover and have the molecule pop up. But we just can't do it at the moment.
Okay, thanks.
Another way, the layout that's being done here by the network, this is using a force-directed layout. You can change the layout algorithm. So there's a bunch of them that are available. For these data sets, what actually tends to be useful, or what often is useful, is to do concentric. And then basically the most interesting compounds end up are almost always the ones at the very center of this. So you can kind of, the compounds rank themselves. The ones that are most interesting are at the middle. Yeah, so that's the view. And what we can do at this point is what comes out of this, I'll leave these three selected. I'm going to apply this as the new default. And what comes out of this are the three rows that I selected. So we had the 70 something, 74 go in, and now the three that come out are the ones that I decided are the most interesting compounds in the data set. Normally what I probably would have done is picked most of that cluster actually, but it doesn't really matter for the purpose of this analysis. I'll show this next, the final output, and then we'll go inside and look at the network view to see how we built that. So then the last step in that is just a review. It's just to show the compounds we picked. So there we go. Those are the compounds and the values attached to them. And now you can imagine, instead of having the output of this, instead of the output being a view, you might want to do something like write this out to a SD file or maybe to an Excel file to share with your colleagues. And Knime has stuff to do that. Let's go in and look in the network view inside this component and see how we did that selection. At this point, it shouldn't be horribly surprising, right? So remember, we have a view that has a range slider up at the top. There's a network view, and then there's a table view. So we should hope that what we're going to see when we expand the component, there's going to be some other nodes, of course, but there should be the range slider, and there should be a network view, and there should be a table view. So look inside, and sure enough, we have a range slider, the table view, and the network view. They are all derived from the same table, so they're all talking to each other, which is what we want. This is now worth getting into. The output of the table view is all the compounds, and it has an additional column at the end, which is selected. And this column has been added, and what it tells you is whether or not that particular row was selected the last time I opened the view and did my selection. So there are sort based on this. There are 3 rows. These are the 3 rows that I selected. So the 3 rows were selected as true, and otherwise it's false. So this is just something added to the table by the interaction that we did. I can then add a row filter where I say, look at the selected column and include values where the selection is true. So when I do that, I have an output table that has those 3 selected rows in it. I now then add a column filter and I take out that selected column because it's not useful anywhere else. And that's what's passed to the output of the component. The network viewer we saw before, the table viewer we've seen before. In this case, the range slider filter definition, I'm not using the output of that because I'm not interested in the output of it. Really, I'm just interested in what is selected in the table view in the end. And as you saw, I can change the selection of the table view by selecting things in the network viewer or by selecting things in the table viewer itself. Good. So that's the last of the components for this. Again, just to review for that, we have the network view, which allows us to select things and see what's selected. Then there's the table, which is showing all the compounds, and the range slider up at the top, which allows us to change what's visible in the network itself. And as I mentioned empirically, I've seen that in general, the most interesting compounds tend to show up with a hub score of above 0.01. Let me change this back to COSA. Good. So you have in the workflow that I sent you, or the data that you downloaded from the Knime Hub, you have the data from a number of other patents. So Aricept, I'm not going to try and pronounce these names, but you have the data from another number of different patents. These were all exported from SureChemBall, so they're nice ones to play around with, just to try the workflow out and to make sure that it actually works for other data sets. I included some in here where this whole trick of using the hub score doesn't work very well. So you can discover those yourself by looking at it. And I think the other thing that's worth mentioning about all of this is up until this point, we did all of this interactively. But because of the way the settings were saved with all of these things, the majority of the data processing, so this is the preprocessed data, there's no interactivity with. This view data we manually filtered, but remember the filtering here was defined with those range sliders. So the output of this is defined by those range sliders, and the settings of the range sliders are saved, as you see. The generate neighbor network is automated. The one piece that's not automated to all of this is this network view and filter. So this is the one step where for the workflow itself, it doesn't make sense to automate because you really do want to look at the workflow. But we could imagine taking this and just saying, sort if we wanted to automate this whole thing, we could add an alternate path for this where we take the nodes that are in the network and we sort them by, I might as well go ahead and do this instead of just describing it. So I'm going to go to the node repository. I want to sort, add a row sorter. Sorry, table sorter. So I showed you a couple of ways already to connect nodes. The obvious way is to collect the output port of one and drag it to the input port of the other. Another thing I can do is select 2 nodes and hit Control L to link them. And now they're linked. I'm going to sort the table based on the hub score in descending order. And we can look at the output of that. And you can see that I have here's my hub score column. Let me put it over here at the end. And this is what we were looking at before in the network view, but you can see the hub score drops very quickly to being at or near 0. So I have now sorted the hub score, and now I'm going to add a row filter. So I have the sorter is selected, so I'll just double click row filter and it'll add it to the workflow connected. Get a row filter, and let's say I want to include rows by number, and I'll take 5. So I take the top 5 rows in the data set, because remember I sorted by a hub score, so this takes the first 5 rows. And now the output is just the 5 highest hub score compounds. So this would be a way to automate the whole process, and I could then write that out to an Excel file. So if I wanted to have this workflow so that I could run it completely automated, I've manually picked the settings for this the first time, and then they're saved with it. I've manually picked a threshold that I think works, and then it's saved with it. And then I execute the workflow, change the file, and I have a manual or an automated way of doing the analysis that we just saw.
I'm not very keen on Excel, to say the least. So could you maybe just show how to export to an SD file or write to an SD file?
Let me make sure I have a useful column in the data. This whole thing is really set up to do, the whole workflow is set up to do for this interactive analysis. So at this point, I don't have a molecule column. So I need to get a molecule column in there. So let's go find the last node that has a molecule column. Okay, this has a molecule column in it. So what I need to do is I need to get the molecule column from here onto the rows from here. I have a row ID that's consistent across these that I can use. So at least I think I do. Let's see if this works. I'm not sure this is going to work, but I want to use a joiner. So and the row ID is not going to work. Let's see, this might work. Otherwise, we're going to have to do a little bit more work here to make this actually go. No. Okay, so the problem here is that I don't have anything coming out that has an ID corresponding to what went in.
Yeah, I guess it would be better to just carry the smile string through, wouldn't it?
Yep. So I'm going to do that here. If I have it. No, but I do. I need to find an ID, an actual identifier that I can use here. Okay. I do know how to. I don't know how far back I lost the smiles column, which is why I'm not doing that at the moment. Because that is otherwise a good suggestion. So I'm going to add a column to this. Called original compound ID. It's based on the row IDs. The row IDs are assigned by Knime when I created this. I need to make sure that that ends up in the output table. And I go back out here, let me execute that again. And what I should have now is a table that has that original compound ID. And original compound ID is equal to the row ID of the other table. Yeah, so I'm not quite sure. This will take a little bit of doing. I didn't set the workflow up to do that basically. So I throw the smiles column out somewhere. So we'd have to.
It looked like you had the smiles column in there, but yeah, never mind.
This does not have it. It's, maybe I took it out here. It's there. I'm not just over. Oh no, there's a smiles column there. I apologize. But it doesn't make it out.
Yeah, well, maybe we can leave this at this point.
Yeah.
I mean, I think from a chemistry point of view, keeping a chemically intelligent description of your molecule is quite useful, I find.
No, I agree with you completely. I'm a bit surprised that it's not actually there.
Yeah.
Oh, there it is.
Okay.
Was I just not going far enough over? No. User error. Apologies. Let me get rid of that. I was stopping at the image and not going one more over to the right.
Okay.
That's pretty embarrassing. Yeah, okay, there's a smiles. Okay, let me get this into an SD file. So to get it in an SD file, we need SD writer. And you can see that this isn't happy because there's no structure column in this. It just has the smiles column. So it needs something that can be treated as an SD. So for that, we need to do something with the smiles. So I'm going to convert the smiles into an RDKit molecule. So it's going to take the smiles column and convert that into an RDKit molecule column. And I'm actually going to generate coordinates for those because we want coordinates in our output file. And now I have, in addition to the smiles, I have the RDKit molecule column. And now the SDF reader, or SDF writer, I can use the RDKit molecule column. I need to tell it where to put this. So let me just put it on my desktop. You pick the properties that you want to include in the output SDF.
Mm-hmm.
So you can include all or none. I'm going to include all. You can choose which property is used as the molecule title. So I think it's good to have molecule title, so I'll use object ID. And then we let this go. And that now created a file out.sdf, which is on my desktop. Hopefully, I did call that out.sdf. Output. Try that again. And then you can see I have an SD file with all of the data from.
That's really good.
So that's relatively easy once you realize you actually have the molecule column already in your data. Apologies that it took me a while to find that. Anything else on that?
No, that's fine. I mean, do you want to just, you said comment on fingerprints and things?
Sure. So the fingerprint you use will change the results of doing this. The RDKit fingerprint node provides a number of different fingerprints that are available. These are documented in what these are documented in that presentation that Chris linked to. I mentioned when I went through this already that the Morgan fingerprint is really, it's what I would pick initially if I just wanted something chemical. I'd pick something where you get chemically reasonable results. There's nothing really surprising in the output. If two molecules are similar by Morgan, they really do look similar. If you're doing other kinds of analysis, it may be that you want, for example, a more fuzzy similarity, and then you can use something like atom pairs, which tend to give, due to the features that they use, the similarity values are fuzzier. So sometimes you get things that are highly similar by the fingerprint that are not similar. They don't look chemically similar. It all depends on really what you want to do with the analysis. But the Morgan with the radius 2 is really, it's a good starting point for an analysis. And for most things, you probably won't need to use anything else, but there are a bunch of different things available. A thing I would not recommend, if you read papers, people often use Max. Max people use because it used to be, there were one or two pieces of software that used it heavily. And it was one of the first of the fingerprints that was widely available. It was used within ISIS. So for dinosaurs like Chris and I, we've seen these, but it's really terrible. It's much better to stick to something like Morgan or the RDKit fingerprint, which is a kind of path-based topological fingerprint. There's a question about similarity. There are many, many, many different similarity metrics, and there is almost no reason to use anything other than Tanimoto for almost any use case. The one exception to that is if you want a similarity metric where you can compare a small molecule to a large molecule and get a high similarity if the small molecule is completely contained in the large molecule. And for that, you would want to use something like cosine similarity, which allows things like that to work. But in general, Tanimoto, there's no reason not to use Tanimoto for basically anything with bit vectors.
Yep. We have a question about the nodes. You mentioned that some of them are freely available, but are not going to be in the future. Does that mean that the workflow will just stop working?
This workflow is purely open source, so everything in here will continue to work. If you use one of the Chemaxon nodes, let me show you where those are. So the nodes here, Chemaxon InfoChem, the Marvin nodes, these are free and have been free for years. Chemaxon, for business reasons, has decided that they're going to require a license for these, starting with our next release. So the Knime release starting in December. There will be a free license available for non-commercial use. So you can write to Chemaxon and they will send you a license and then you can use it. But that's for non-commercial use. Anybody else will have to get a license from Chemaxon. The workflow that I gave you doesn't use any of these nodes, so it'll be fine even if you don't have a license for the Chemaxon stuff.
Okay, great.
I guess sorry, if you do have one of these incorporated in your workflow and you don't have a license, what will happen is any node that any of these nodes or anything downstream from any of these nodes will not work.
Okay. Could you maybe just give a view for what size data sets you can work with?
That's a difficult question to answer. So it really strongly depends. It is not a problem to effectively in our field, depending upon what you're doing with the data, there's not really a limit on a modern computer. So it would be, I'm running this on a laptop, it would be no problem for me to run a data set that has 1 million rows in it, or 2 million rows. If I have 2 million rows and 1,000 columns, so each table is really big, it'll take a long time to run, but it should work. There are some operations, however, that require the entire data set, and those will be a problem. There are also some data sets, some operations that are n squared. So you look at like for example, distance matrix. The amount of time it takes to generate a distance matrix scales with the number of rows squared. So we have about 100 rows here. If we go to 1,000 rows, it's going to take 100 times longer, right? If we go up to 10,000 rows, you can do the math. It goes up really quickly. So, but that's not a limitation of Knime. That's just if you're using an n squared algorithm, when you increase the data size, the runtime goes up. So practically on a modern computer, I don't encounter problems with data size in Knime. Knime is good about using the disk if stuff doesn't fit in memory. It really is not a problem.
Yeah, there's a question about the different versions of Knime. Someone is using Knime 4.1.3. Are there nodes that don't work with particular versions or anything like that?
That depends upon the node author. So the nodes, okay, let me say first some stuff about backwards compatibility. Knime maintains backwards compatibility. So if I had created this workflow in Knime 2.5, it would still open, and I'm using Knime 4.2. So backwards compatibility works. Forwards compatibility does not always work. So I created this workflow in 4.2. It probably won't open in 3.7, or it'll only open with problems in 3.7. So Knime itself, the way we save files, we maintain backwards compatibility. There are times that we break forwards compatibility, and I think that's fine. There are, however, so as we go from one version to the next, we do occasionally add new nodes. So for example, this workflow uses the remove duplicates node. So the duplicate row filter node. This was added in 4.0 or 4.1, I don't remember which, I think 4.0. So if you were to open this workflow in an older version of Knime that doesn't have this node, what you will get is the workflow will open, but you'll end up with a hole in it. You'll have an indication that there's a missing node. So basically opening it in an older version, it sometimes will work, it doesn't always work. But this should be fine in 4.1. This one, I think, should be fine in 4.1. I don't think I'm using anything super new. And stuff from 4.1 might work in 4.0, though we'll have some problems, and going back to 3.7, there's going to be problems.
Okay.
But not the other way. 3.7 will open in 4.2, no problem.
A question about how do people contribute nodes?
So the easiest way to contribute nodes is we have an active community, and you can do community extensions. So here in Knime itself, you can see the community nodes. I only have 2 sets installed, so I have the RDKit nodes and the Vernalis nodes installed. If you develop a set of nodes that you want to make available to other people, and you want to do that easily through Knime, you can get in touch with our community group, and they can explain to you how to do that so that your nodes show up in the community nodes. If you develop a set of nodes yourself and you just want to distribute them, you are welcome to do that. It's easy enough to do once you figure out how to develop Knime nodes. You would provide an update site that has those nodes, and then people can download them from your website and install them in a Knime manually themselves. If you want to do components, so for example, I could share this component with somebody by exporting the component or just copying it to the Knime hub. So we talked briefly about the Knime hub. If you're in a modern version of Knime, you have this My Knime hub thing. You need to log into that. You need to have a Knime forum account. These are free. So if you register with the Knime forum, it automatically works. Otherwise, you just need to register with the Knime forum, and then you have an account and you have a space on the hub. And then you'll see the same thing here, public and private. You can have a components folder, and in that components folder, I can say here, I want to have this component and share it via the hub. I'm not going to get into the details of what exactly is happening here because that takes too long, but you can now see this view data component is available via the hub. If we go to the Knime hub itself now, so this is where I was pointing to you to before. This is in my space on the hub. I can go back there and go to public, go to components. There's view data. I can then drag and drop this directly onto a workflow, and it'll download it from the hub and add it to the workflow. So that's really easy. If you do components, it's very, very easy to share them via the hub. I just showed you how. The green arrow here indicates that this is linked back to the hub. So every time I restart this workflow, it will ask you if you want to have it check the hub to see if the workflow has been if the component has been updated. So if I were to leave this on the hub and wanted to support it, I can make updates to it on the hub, and then anybody who's using it can choose to have their local workflow updated with the most recent version. Or I can say I don't want it linked anymore, and I can just tell it to disconnect, and now I just have a local copy of that component.
There's a message from Roger Sales saying that the workflow doesn't open in 3.7.
Yeah, no, it doesn't open in 3.7. So Roger, we're backwards compatible, but not forwards compatible, and certainly not that far.
Yeah. Okay.
Actually, I think this workflow, I created this workflow in 4.2, so it probably won't open in 4. It may not open in 4.0 either. It should open in 4.1 though.
Yeah. I think and apparently it's just upgraded to the latest Knime.
Thank you, Roger.
So I don't think we've got any more questions. There's a lot of people saying how much they've enjoyed the webinar, and I hope that you're going to get a lot more new users because of this. Just to let everybody know, all participants will get a copy or a link to the videos in due course. But at the moment, I'd just like to thank Greg for another fantastic presentation. I think Knime is one of these things that once you get used to using it, becomes absolutely invaluable. And it's a fantastic resource to have as an open source project.
Thank you.
If there are no more questions, I shall close down the webinar now, and everybody can go and have their lunch or tea, dinner, or whatever it is. Thanks very much, Greg.
Thank you.
Bye-bye.